Welcome back. Let us discuss the details of the memory system. Let's start with a mathematical model of what the CPI of a processor will be if we have a memory system with caches and cache misses. Then we'll discuss the different kinds of misses and what can be done about them. So let us compute the CPI of a pipeline that has misses in the cache hierarchy. So let CPI be the actual CPI. And let CPI ideal be the CPI with an ideal memory system where every memory access takes one cycle and every memory access is a hit. So if this is the ideal CPI, let the stall rate be the number of stalls that we have uh, per instruction, right? So per instruction, what is the rate of stalls that we have? So for example, if let's say for every 10 instructions, one of the instructions stalls, then the stall rate is 1 in 10. And let stall cycles be the number of cycles that we waste because of the stall. So let us assume that if say the ideal CPI is 1, which is the case of maybe a single cycle line, a single cycle processor, the stall rate is 1 in 10, and for every stall we on an average we waste 3 cycles. Then the CPI is 1 plus 3 by 10, which is 1.3. So this can also be said, this is CPI ideal. So the stall rate, so if we assume that every instruction that goes to memory can potentially stall, so we can then say that the stall rate is, so we can equate this and this. Fmem is a fraction of memory instructions and the number of stall cycles. So if let's say all the memory instructions hit in the L1 cache, then the stall cycles is 0. But let's say on an average, if for all the memory instructions, the average memory access time, AMAT, instead of 1 cycles is 1.1 cycles, then we compute the number of stall cycles as the average memory access time minus the time it takes to perform an ideal access, which is 1 cycle. So in this case, it is 1.1 minus 1, which is 0.1. So as a result, and assume that if let's say 30% of the instructions are memory instructions, so the CPI will be CPI ideal plus 0.3 times 0.1. So let me discuss this equation in a different light. So what we are essentially trying to do here in the first line is that we are trying to compute the CPI with a non-ideal memory system. So for that, what we do is first we get the CPI for an ideal memory system. So this can include pipeline stalls and everything else, but the only assumption here is that the memory system per se has hits in 1 cycle. Then we use the parameter stall rate as the fraction of instructions that actually stall, and for each stall how many cycles is it that we waste. So this essentially gives us the number of pipeline bubbles. So as we have seen in the previous chapter, we can compute the CPI in this manner. So what we do now for the memory system, we take this term over here and replace it with an equivalent term, which is this. So we consider the fraction of memory instructions in the program and multiply them and multiply this fraction with the average number of stall cycles per memory instruction. So this will give us the total stall cycles per instruction. And so the average number of stall cycles per memory instruction is the average memory access time minus 1. Why minus 1? The reason that we subtract 1 is because we assume that every memory instruction will take 1 cycle And this one cycle is folded into this CPI over here, so we need not do double counting. And consequently, we can compute the stall cycles for memory instructions as AMAT, average memory access time, minus 1. And if we multiply the average stall cycles per memory instruction with the fraction of memory instructions, we will get the average stall cycles per instruction. So then we will add it to the CPI. So essentially, one thing that we see is that as the fraction of memory instructions increase, the CPI will increase, the performance will go down. And similarly, the memory access time increases, then also the CPI will increase. Now, why will the memory access time increase? It will increase if there are more misses in the cache hierarchy. We need to go lower in the memory hierarchy and we need to fetch data. This will increase our overall access time and this will increase our CPI. Consequently, make the processor run slower. Now let's try to compute the average memory access time. So the average memory access time can be computed as follows. So let's take the hit time. So every instruction needs to go via the L1 cache. So let's consider the hit time of the L1. So this will be added for every access irrespective of the fact whether it's a hit or a miss. So a fraction of the accesses that go to the L1 cache will actually miss in the L1 cache. And for all of those misses, we need to pay a miss penalty, which is the number of cycles it takes to go down the memory hierarchy and fetch a value and write it back to L1. So the L1 miss penalty can further be broken down as follows. So the L1 miss penalty corresponds to this quantity. So let's take a look at it. So the average memory access time is again the L1 hit time plus the L1 miss rate multiplied with. So in the L1 miss penalty, all the accesses that miss in the L1 cache go to the L2 cache. So we have a similar formula for the L2 cache. For every L2 access, we have L2 hit time because irrespective of a hit or miss, we will take some time to figure out whether it's a hit or miss. So this is the L2 hit time. Plus, we will have, some of these accesses will again miss in L2, so it'll be L2 miss rate. And similar to an L1 miss penalty, we'll have an L2 miss penalty, which is the number of cycles it takes to go down the memory hierarchy and fetch a value. So, this is pretty much the formula for the average memory access time. And of course, we can go down, so I'll have that in the next few slides. But the important thing to note here that irrespective of a hit or a miss, we need to spend some time. This is the hit time. And then, a fraction of the accesses will miss. And for the misses, we need to pay a miss penalty. So when we are actually computing the stall penalty, which is the quantity in the previous uh, equation, which is pretty much this, the stall penalty. This is so if you consider, I'm sorry, it's not this quantity, it is this quantity. This it is this quantity. So this quantity will be the average memory access time minus the L1 hit time. So the reason that we define it like this is because we assume that in an ideal in an ideal processor, all the instructions will hit in the L1. So the L1 hit time will be folded into the computation of CPI ideal. So we need not consider it again in the sense we need not consider it as a penalty. So as a result, it should be ignored. So it's not a stall penalty, right? So it should be ignored when we are computing the stall penalty. The stall penalty will essentially be the average memory access time minus the L1 hit time, which means that this quantity over here is the stall penalty. And this quantity can further be expanded as L1 miss rate times L2 hit time plus L2 miss rate times L2 miss penalty. So what we can do is that we can further extend this equation. So as we had shown in the last slide, the average memory access time is the L1 hit time plus the L1 miss rate times the L1 miss penalty. The L1 miss penalty further is the L2 hit time plus the L2 miss rate times the L2 miss penalty. So, every single term is getting defined like this. And furthermore, the L2 miss penalty is after the L2, if you have an L3 cache, is the L3 hit time plus L3 miss rate times L3 miss penalty. So if we have n levels in the memory hierarchy, right, n levels of caches, so for the last level, so for the second last level, the Ln minus 1 miss penalty will be the Ln hit time because we're assuming that the last level of the memory hierarchy contains all the lines and as a result its miss rate is 0. Right? So this is the main memory that we have been talking about. Its miss rate is 0. So basically this quantity, this miss rate quantity over here becomes 0. So as a result, for the last level, the miss penalty of the second last level is the hit time of the last level because we are assuming that no accesses miss over there. So this further tells us that if we know the miss rates at each level and also the hit times at each level, we'll be able to compute the average memory access time. Let me now define some terms. So the miss rate that we have been using is called the local miss rate. So it is equal to the number of misses in a cache at level I divided by the total number of accesses at level I. So let me give an example. Let us assume that we have an L1 cache and we have an L2 cache. Let's assume 100 accesses go to the L1 cache and then 90 of them have a hit in the L1 but 10 go to the L2 and from the L2 to the main memory 5 accesses go. So at the L2 the local miss rate is essentially, so it gets 10, so it has 5 misses and it gets 10 accesses, so the local miss rate is 50%. In comparison, we can define the global miss rate. It is equal to the number of misses in a cache at level I divided by the total number of memory accesses. So the global miss rate will essentially be, for the L2 cache, 5 divided by 100. So what is typically of more importance is the local miss rate, which is 5 divided by 10 or 50%, and that's what we have been using in all our formulae. But it's still important to know this term global miss rate, which is the misses at a certain level divided by the total number of memory accesses. Now let's define the term called working set. So before I define that, I want to talk about how typically a program works. So the way that a program works is we typically have multiple for loops and while loops. So we have a lot of iterations and then we move to another section of the program. Again, we have a lot of for loop iterations. We move to another section and so on and so forth. So maybe in this part, we will access one array or a group of arrays. So for a certain fixed period of time, we'll be accessing some data. Again, we'll move to another part of the program, we'll be accessing some other data. So in a given time interval, the amount of memory that a program accesses, this amount of memory is called a working set. It's called the working set of the program at that particular point in time. So for example, let's assume that a given program accesses typically 1 megabytes or 2 megabytes of data and it does not access more than that. We can say that the working set is 2 megabytes. Let's assume that one more program accesses 2 megabytes for some period of time, then in another period of time it accesses 4 megabytes. It accesses 4 megabytes meaning that it has loops that sort of scan through that entire 4 megabytes of data, and then again it accesses 2 like that. So we can say at this point of time the working set is 2 megabytes, at this point the working set is 4 megabytes, at this point the working set is 2 megabytes, and so on. So essentially, this is again an approximate definition, there's nothing formal about it, but roughly in a small time interval in the execution of the program, the amount of memory that is accessed is called as the working set. So what we want is that we want the working set to fit in the caches such that most of the data that a program would require would be available in the caches. Now, given the fact that we have seen this, let us look at misses and what can be done to them, done with them, and let us try to classify the types of misses that happen in a in a memory system. So these are called the three C's actually, because there are three kinds of misses. All three start with the letter C. So these are called the three C's. So the first category of misses are compulsory misses. So these are misses that happen when we read in a piece of data for the first time. So they're also called cold misses. So compulsory misses or cold misses will happen when when for example when the program is starting up, uh, the none of the data will be in the caches, so we will need to read it for the first time, and these misses have to happen. So they are called compulsory misses, also called cold misses, because essentially when the program starts, it's cold. Next, we can have conflict misses. So a conflict miss is like this, that these are misses that occur due to a limited amount of associativity in a cache. So for example, assume that a cache is four-way associative, which means that in each set there are four ways or four entries. The access of the program is such that maybe you very frequently access five separate addresses and five separate cache lines that are mapping to this set. So since this set can only contain four entries and there are five accesses to five separate blocks or cache lines, same thing, uh, one of them will need to get displaced, the other one will come in. So we'll have a lot of these evictions because only four out of those five can be accommodated. So we'll have a lot of evictions. And what is happening? There is a conflict. There is an address conflict inside a set. So this is known as a conflict miss. So the last category of misses are capacity misses. So assume that the working set of a program is 10 kilobytes and the size of the cache is 8 kilobytes. So in this case, the entire working set will not fit. So assume that there is a 10 kilobyte long array and we are doing a lot of operations on that array, but our cache is only 8 kilobytes. So the entire array will not fit, and as a result, we'll have a lot of cache misses. So this is called a capacity miss. So what are the three kinds of misses again? We have compulsory misses, which happen when we are reading in a program for the first time, and we'll have a miss. We'll have conflict misses, which are basically because our cache ways have limited associativity, and hence we'll have some conflicts because we cannot store a lot of blocks in one cache. We're limited by the associativity, and as a result, if something new comes in, something old has to go out. And we'll have capacity misses, where if the working set exceeds the size of the cache, then we'll have evictions, replacements, and consequently higher cache misses. So let us look at schemes to mitigate misses or to reduce the number of misses. So compulsory misses, so what is the idea? One way of reducing this is we can increase the block size. So let's say instead of a 64 byte block size, I make it a 128 byte block size. Then this means that in one go we are fetching in more data from the lower level. And because of spatial locality, the reason that we made blocks in the first place, it is possible that the number of misses might go down because you will access a lot more data you'll find within the same block. And this would not have been possible had the block sizes been smaller. So let me give an example. So let's assume the block size is 64. So we fetch in 64 bytes. And after that, we need to access the next 64. This is not there in the cache, so we'll have a cache miss. But assume that we fetched both the 64 consecutive 64 byte blocks together and your block size is 128, then essentially all the 128 bytes are available in the block. As a result, we will not have, the cache miss that we had for the second block. So this can work. The other is, let us try to guess, let us have a small circuit that tries to guess the memory locations that will be accessed in the near future. So, maybe if you're accessing an array, so let's consider a typical array access. So we are considering, sorry for drawing a slanted array. Uh, so let's assume that we have one program, it's sort of trying to do bubble sort. So then we are accessing the array elements sequentially one after the other. So if you have a small circuit over here which is sort of analyzing the array accesses, analyzing the addresses of the array, it will be able to predict that if we have reached this point, then most likely, and since we're accessing them in sequence, so most likely we will access the next few locations. So it can guess that the next few locations will be accessed because we are going consecutively, you are going in increasing order of array locations. So it can guess and fetch them from the lower level in advance, and this is called prefetching. Prefetching means guess, predict what you will access in the future, and fetch the data from the lower levels of the memory system, which means that if we have an L1 cache and we have an L2 cache, and we have a small prefetching circuitry over here, so it can look at all the accesses that are going into the L1 cache and on the basis of that make a guess that what kind of accesses are required. So it can then put in requests of its own to the L2 cache, and that data will be again be supplied to the L1 cache. So hopefully this can reduce the number of misses in the L1. Now let us talk of a scheme to reduce the number of conflict misses. So in this case, the simplest solution, the simplest solution is to increase the associativity of the cache. See, if it's so because the problem is essentially coming because of associativity. If we have a limited four-way associative cache and 5 lines are mapping to the same set, we will have misses. So let's increase it from four-way to eight-way, which means have eight entries in each set. Well, this is easier said than done because more are the number of ways, more is the power consumption because of more comparisons, and more is the latency. Again, because of the fact that we have more circuits and there is a certain slowdown that is induced. What we can do instead is that we can use a smaller fully associative cache called a victim cache. So the idea of a victim cache is like this, that any line that gets displaced from the main cache can be put in the victim cache. So what we can have is we can have an L1, we can have an L2. Of course, they are communicating, but we can have a very, very small cache over here called a victim cache. And we can have many heuristics to put data here, but essentially anything that is being thrown out of the L1 cache can be put in the victim cache. It's a victim, so it can be put over here. And subsequently, any read access needs to check in both the L1 and the victim. And once when the victim fills up, we can evict something here and we can make it be sent to L2. So there are certain advantages of the victim cache. I'll discuss this in the subsequent slides. Let's take a look, but before discussing that, let me take a look at the third point, which is to write programs in a cache-friendly way. What this basically means is that we can, either at the level of the programmer or at the level of the compiler, we So this is mainly at the level of the compiler actually. So when I say write programs, it's not that much from a programmer's point of view, but it's from the point of the view of the compiler. That allocate your data structures in such a way that they are fairly balanced across all the ways of the cache. So all the sets of the cache. So no set is unduly stressed, right? There is no amount of undue traffic on each set, and this will reduce. This will sort of reduce the pressure on any one set and decrease the number of misses. So let's discuss the victim cache in a little bit of more detail. So let's consider the first case where we send a request and we find the data in the L1 cache, right? So basically in this case nothing needs to be done. We read the data in the L1 cache and the data goes back to the processor. Now let's assume that we don't find the data in the L1. So why will we not find the data in L1? Because it's not there. But let's assume that previously some line was thrown out from L1. Instead of writing to the L2, we wrote it to this small fully associative cache called the victim cache, which is small and fast. So in this case, we first check in L1 or we check in L1 and victim parallelly, it doesn't matter. And if we find it in the victim cache, we take it and we give it to the processor. So once again, we find the data in the victim cache, we take it and we give it to the processor. If we don't find the data in the L1 and the victim, well then we need to go to the L2 cache and give it to the processor. So what's the advantage of a victim cache? So the advantage is like this, right? So there is so let's look at maybe some sizes. So the L1 is 8 kilobytes. The L2 is 128 kilobytes. The victim cache might just contain 8 entries. And if one entry is 64 bytes, so 8 entries will be 512 bytes, or essentially half a kilobyte. So half a kilobyte is not really a lot, right? It's not, tremendously increasing the size, but it can make a fair amount of difference. And the reason that I say so is like this. So let us assume that, as we have been seeing in a running example, we had 128 entries. So if we have a two-way associative cache, so we'll have 64 sets. So if we have 64 sets, so let me maybe draw them. So let's consider a two-way set associative cache with 64 sets, and each set has two lines, right? Each set has two cache blocks. So the ideal case would be when the entire access is balanced. So each of the set gets roughly a similar number of cache accesses. However, if that is not the case, then what should be done then what will happen is that maybe there will be some such sets which are pretty unlucky. So it maybe could be this one and this one, where it has a fairly large number of accesses, a disproportionately large number of accesses go to these two. So there will be a fair amount of conflicts in these two sets, and there will be some conflict misses. So if some of those lines can be accommodated in the victim cache, so the victim cache, mind you, has half a KB of size in this case, then we can sort of logically think that for some of the sets that have high contention, we have in a sense increased their size. Or in other words, what it means is that for some of the frequently accessed lines that we still have to throw away from our cache because of limited associativity, we'll find another home called the victim cache, which is again a very small and very fast structure. And this will hopefully have an effect which is far higher than what its size would otherwise predict. For example, a half a KB cache, when especially sandwiched between an 8 KB and a 128 KB cache, will have a minimal effect. But if we design the algorithm to send cache lines to a victim cache slightly judiciously, and mainly target lines that are evicted from highly accessed or highly contended sets, then most likely these lines will be accessed more frequently in the future because of temporal and spatial locality effects. And as a result, the victim cache might actually play a significant role in appreciably reducing the number of accesses that go to the L2 cache, the number of memory requests that go to the L2 cache. So as a result, a victim cache can prove to be very useful because it's not significantly adding to the access time. And L1 cache takes one cycle to access, and we access the L1 and the victim parallelly, or we access the L1 first and the victim later. We will still, the access time to victim cache will still be around, additional 2 cycles. But as compared to that, an L2 cache can take much longer to access, somewhere between 10 to 15 cycles. So there is still a significant amount of speed up, and the victim cache can capture those lines which are otherwise frequently used, but because of conflict reasons, all of them cannot be accommodated in the same set. We will definitely see some benefit. That's the reason the victim cache idea is very popular, and it is used. It is used. It is a very common artifact in modern processors. Now let's discuss some other schemes to mitigate misses. So let's look at capacity misses. So we have already discussed compulsory. So what was the scheme for mitigating compulsory misses? It was either increase the block size or prefetch. The scheme to mitigate conflict misses was increase associativity. That is easier said than done, because a higher associativity means more latency, more time, and more power. So in comparison, a victim cache could be used, and the victim cache, as we just discussed, if we can design an algorithm. So there are many algorithms in the literature. So there are many in research papers which essentially um, ensure that some of the most frequently accessed lines which cannot be accommodated in L1 cache find a place in the victim cache. We can see significant improvements in the performance of the memory system. All right. So for capacity misses, we again have a simple algorithm. The simplest thing is increase the size of the cache. That is again easier said than done. The reason being that a larger cache is also slower and more inefficient in terms of power. Or we can use better prefetching techniques. So in this case, what can happen is if we can predict and fetch what is needed in the future, so hopefully that will sort of reduce the impact of having a smaller cache. But prefetching is per se not a part of this course, it's a part of an advanced course in computer architecture. So let's now discuss some thumb rules. So the first, so what is a thumb rule? Well, a thumb rule is something that people have observed. A thumb rule is something that people use, but it does not have a theoretical proof. It is just, something that has come from observation. And that's the reason it's called a rule of thumb. It's not a proof. I mean, it does not have a proof. So one thumb rule is that the miss rate is proportional to the inverse of the square root of the cache size, right? Which means that this is called a square root rule. So which means that if I double the cache size, uh, or if I increase the cache size by 4 times, then I'll reduce the miss rate by a factor of 1 by 2. So I'll reduce it by 50%. So the miss rate is 10%, and I want to make the miss rate 5%, I need to increase the cache size by 4 times. So, as I said, it's an approximate rule. So, might not be 4 times, might be 3.5, might be 5.5, but it's a good strategy to at least remember. The other is the associativity rule. So this is again also approximate, no theoretical proofs, just has been observed. Observed in simulations in actual processors, and it's also very approximate in nature. So the associativity rule says that doubling the associativity is almost the same as doubling the cache size having the original associativity. To give an example, a 64 KB 4-way cache will roughly have the same miss rate, very similar miss rate, as a 128 KB 2-way cache, right? So what are we doing? We are doubling the cache size and we are reducing the associativity by half, right? And so in this case, or if we go from this way to this way, doubling the associativity uh, from 2-way to 4-way is the same as doubling, keep the original associativity but double the cache size. So, these two rules are approximate, can be used, uh, you know, whenever required. Let's now move to the next slide where we will look at what is called software prefetching. So there are two kinds of prefetching algorithms. One is software prefetching and the other is hardware prefetching. So in hardware prefetching, what happens is that we have a hardware circuit that looks at the memory accesses and then tries to guess what we'll access in future, and it tries to fetch that from the lower levels of the memory system. We can instead do it in software and it's very easy. So we can actually augment our C code to fetch things from the memory system in advance, well before we actually use them. So let's take a look at this program over here. So in this particular function, what we try to do is that we consider an array. So we consider a data array and we consider an array with the indices called the array vals. So we iterate through each and every entry of the vals array. So we assume that there are n entries where n is a predefined global constant. For each of the n entries starting from 0 till n minus 1, we access each entry of the vals array. And in each entry of this vals array, what we do is that so we assume that each entry of the vals array contains an index. We take that index and we access the data array, and whatever number is stored over there, we add it to the sum, and finally we return the sum. So this is called the add all function. So we analyze this function, we'll realize that this function neither has temporal locality nor does it have spatial locality. So why doesn't it have temporal locality? Well, so this will again depend on what is contained within the vals array. But if it contains fairly random elements, so the same elements or similar elements, similar blocks are not being accessed frequently over time in the same period of time. So as a result, temporal locality is not there. Spatial locality is also not there because consecutive elements or elements with nearby addresses are also not being accessed. Well, the vals array is being accessed, so there is spatial locality in terms of accessing the vals array, but not in terms of accessing the data array, right? So the vals array, we are accessing vals 0, then vals 1 and so on. But assume val 0 contains 10, vals 1 is 32, vals 2 is 120. Then the addresses that we are accessing are 10, 32, and 120, which are absolutely random. So for the vals array, we have spatial locality because they are increasing orders of array indices, but not for the data array. And for the data array, we pretty much have very random addresses. And so as a result, even spatial locality and temporal locality both are not there for the data array, even though they are there for the vals array to some extent. But because entries are being accessed randomly in the data array, we'll have a lot of cache misses. So this means that such kind of code, where we have a double indirection, in the sense the index of the data array is itself an array element. This is common. This is very common in scientific code. It's very, very common. And it's called an irregular array access. and this typically has a very bad cache performance. So what we can do is that we can add one line which will make our cache performance fantastic, and it'll some experiments indicate that the performance of a program can even increase by 3 times. What we do is that if you're using the GCC compiler on Linux, right, this thing only holds for GCC on Linux, can hold for GCC on Mac also, but I have not tested. We can use the function underscore underscore built-in underscore prefetch. So this is a software prefetch instruction in the sense that it given an address, it tries to prefetch that data and tries to bring it to the highest levels of the memory system, which is the L1 cache. And if the address just in case is wrong or is invalid, it does not matter. So there are never any problems if the address is invalid, right? So that does not create any problems at all. So what we can do is that we can prefetch some address which will be accessed in the future. For example, we can prefetch this address over here, which is vals I plus 100. So assume that in a current iteration, we are at vals I. So after 100 more iterations, we'll be accessing the data array entry at vals I plus 100. So we can prefetch that entry in the current iteration by calling the function underscore underscore built-in prefetch. So what this does, so the way that this works is that we send a pointer to it, and so the AND operator in C essentially creates a pointer, and it gets the address, the memory address. So we get the memory address of this element and we send it to the memory system such that the the and from the lower levels of the memory system, we can the data we can get the data back up to the upper levels. This instruction, of course, we're adding an extra instruction, so the performance penalty is there. But hopefully, by prefetching data in advance, it will become very easy. Not very easy, but by prefetching data in advance, when we actually access the data later, we'll find it at the upper levels of the memory hierarchy, and the miss penalty or the memory access time will be much lower. So this is actually the case. So if you just run this program, I invite all the readers, all the listeners to write this program and test it for themselves. So you'll also find some of these programs on the website of the book and definitely inside the book also. So if these programs are written and they are tested, so you will find that there is a 200 to 300% improvement in performance, mainly because we are prefetching data. And particularly this pattern is hard to prefetch in hardware because the hardware has to guess that all the indices that are going into the data array are actually coming from another array called vals. And that's pretty difficult for the hardware to guess, even though it is possible. There are research works in that respect. But doing this in software is still easier. It's slightly more intuitive. And so what we do is that for any iteration, we prefetch data that will require 100 iterations later. So readers can ask a question that when we are towards the end of, when we are close to n, then that value plus 100 will be an invalid value. That is correct. But we can always pass an invalid address to built-in prefetch. It will not cause any problems. It will not cause the program to shut down or have a fault or a segmentation fault. So these issues will not happen. So we are pretty much safe. Now let's consider hardware prefetching. So in hardware prefetching, we have a prefetcher that takes a look at, well, it can take a look at two pieces of information. So it can either take a look at, let's say, the accesses to the L1 cache. So that's one thing that it can look at. Or it can look at the misses that are happening in the L1 cache, okay? So basically it can be any one of them, but looking at the misses is slightly more common. On the basis of that, the prefetcher can decide which are the addresses that the processor will most likely access next. It can then send a message to the L2 cache to get in those lines to the L1 cache such that the processor will find them ready and available. So the hardware prefetcher, it works in some cases where the access stream is predictable. If that's not the case, then we need to use software prefetching. There are other things that we can do to make the processor faster by essentially reducing the memory access, average memory access time. So we can reduce the hit time as well. So to reduce the hit time, we need to use a smaller and simpler cache. But well, having a smaller and simpler cache has other negative effects as well. And the main, the biggest negative point here is of using a smaller and simpler cache that it reduces the hit rate as well. So this trade-off needs to be kept in mind. Additionally, we can try to reduce the miss penalty. So the miss penalty can be reduced as follows, that let's consider write misses. So if we consider write misses where we might write to successive words in the same line, what we do is that we create a small write buffer with a very small structure, 4 or 8 entries just after the L1 cache. So we send, so the write buffer need not be after the L1, it can be between the processor and L1 as well. So it does not matter, the concept is the same. So we send the writes to a fully associative write buffer on an L1 miss. And so basically this essentially contains multiple blocks. Uh, so then we do a write. So basically what we do is that if you're writing to 4 bytes, so we write some part of it, but the rest of the block we don't know because the data has not been fetched. Once the data is fetched from the L2 cache, we populate the rest of the contents of the block. So the insight here is that we need not send, and also, at that same time, if let's say another request comes, so maybe, let me just expand this, sort of put a magnifying glass. So let's consider each block to be a 64 byte quantity. So let us assume that the processor wants to write to some 4 bytes in the middle. After that, the processor wants to write to another 4 bytes over here. So, a stream of writes are coming. So a naive approach would be that we first get the data from the L2 cache, and then we pretty much write it to the write buffer. We get the data from the L2 cache to the L1 cache, and then we do the writes. But this will take time. So what we can instead do is that the writes can go to an entry in the write buffer. So let's say we can write to, we can allocate an entry and write 4 bytes. Similarly, if another write comes in the same for the same block, we can write the other 4 bytes, and we can wait for the line to come from the L2 cache. Once it comes, we would have known that this chunk and this chunk have already been written too, but the rest of the contents of the block can be filled with whatever comes from the L2 cache, right? Which is essentially this entire dotted region. So the advantage here is that we don't have to wait, and we can do our writes and then we can proceed with the next instructions, right? So in a certain sense, it reduces the miss penalty of the L1 cache, especially when it comes to writes. Let us now look at reducing the read miss penalty. These two optimizations, critical word first and early restart, are used together. So the insight is something like this, that the memory word that causes the read write miss. So basically, let me go one step back. So let's consider the size of a cache block. So the size of a cache block is typically 64 bytes. But when we read an integer, that might only be 4 bytes. So basically, in these 64 bytes, if let's say we wanted to read an integer and we didn't find it in the L1 cache, we would only be interested in 4 bytes, right? Even though the entire block needs to be fetched, as an atom, as an indivisible unit, but we are primarily interested in 4 bytes. So what we can do is that we can slightly tweak the system here. So consider the L1 cache and consider the L2 cache. So if the L2 is supplying 64 bytes to the L1, And so how will it supply? So essentially there are some copper wires between L2 and L1, and it can take multiple cycles. So, typically we can only transmit something like 4 bytes at a time. I'm sorry, 16 bytes at a time. That is, so it'll take around 4 cycles to transmit. So what we can ensure is that the memory word, 4 bytes of the memory word, so the memory word that we are interested in is transmitted first, right? So maybe we can divide the 64 byte chunk into 16 byte smaller chunks, and maybe the memory word that we have is present in this 16 byte chunk, so we can transmit this the first. Once we transmit it, we can go for an early restart, which basically means that the L1 cache can fetch the 4 bytes within this 16 byte chunk and send it to the processor such that the processor gets its data and it can restart its execution. Alright, so the processor does not have to stall. The advantage here is that we are able to get a little bit of mileage or leverage, little bit of mileage out of the process. And the way we are doing it is that we are tweaking the order in which the bytes get transferred from the lower levels of the memory hierarchy to the L1 cache. And instead of reading the bytes sequentially within a block, we read that part that we are interested in and transmit it the first. After it reaches the L1, we immediately give it to the processor such that the processor can restart its execution. So this is a simple slide that summarizes all our techniques. So this is like a one-stop place for all our techniques. So let me just go over it. So for compulsory misses, we realize that the best technique is a large block size. Because if you have a larger block size, you are fetching more data at once. And because of spatial locality, some of it might be useful. Prefetching both software as well as hardware is a generic technique, very useful. Can be used to reduce actually all kinds of misses, but primarily capacity and compulsory misses. So it is involved with a little bit of extra complexity, and so it reduces the risk of displacing useful data. But nevertheless, prefetching done wisely has its benefits. We can increase the cache size, this will reduce capacity misses. But larger is the cache, higher is its latency, higher is its power, and higher is its area. So that's the negative points. To reduce conflict misses, we can always increase the associativity. So no doubt it will reduce conflict misses, but it will make the cache more complicated. We need to compare with more tags. So this is associated with higher latency and higher power. The victim cache is almost always a good idea. And the reason it's almost always a good idea is because it's very small. So it does add a little bit of extra complexity, but the overhead is minimal. And but its effectiveness can vary depending on the type of the program, but it primarily reduces conflict misses, especially when some sets get a lot of traffic. In that case, if we can save some ways in the victim cache, we'll get some benefit. We can also use compiler-based techniques to reorder the code such that cache misses get reduced. So this is anyway an advanced topic, it's out of the scope of this book. It's not very generic, but it's extremely effective. So after talking about the three C's, the three kinds of misses, let's talk about hit time. So if we want to reduce the hit time, we go for a smaller and simple cache, but again this increases the miss rate, so there's a trade-off here. Let's consider the miss penalty. So for writes, we can reduce it with a write buffer. So here what we do is that we write to the write buffer and we just move on, we continue our execution. When the word comes from the lower level, the new data is merged with the older data. So it sort of helps us go ahead. And while reading, we need to check both the write buffer as well as the original cache. And for read misses, we have a combo of these techniques, early restart and critical word first. So there is some amount of extra state, some amount of extra complexity, but the advantage is that it allows the processor to go ahead because we give a preference to that data that originally caused a miss, right? The 4 bytes or 8 bytes the processor wanted to read and it caused a miss. So if we give preference to that data, it helps us restart the execution of the program sooner. So now that we have seen the details of the memory system, we'll go to the last part, the fourth part of this lecture series, which is on virtual memory.